Alright, let's look at reactions of carboxylic acids. So carboxylic acids and esters are very similar in reactivity. Esters are slightly more reactive than carboxylic acids, but they're both going to be more reactive than amides and nitriles, and they're going to be somewhat less reactive than acid halides and acid anhydrides. And so if we look with strong nucleophiles, carboxylic acids tend to react in an acid-base reaction, and so it's a little bit different than the other functional groups that we've seen, and it forms this carboxylate, which is even less reactive than either a nitrile or an amide. And so it's really going to take something powerful nucleophile wise, like lithium aluminum hydride, to get that to react. So typically it's rare to see that as an effective reagent for the reaction of a carboxylic acid, a very strongly basic nucleophile. However, for weak nucleophiles that are protonated and often neutral here, we have the need to activate the carbonyl with catalytic acid. Okay, so we'll protonate the carbonyl, then that'll make that carboxylic acid reactive enough for even a weak nucleophile to add a byproduct. Kicking off of water is pretty typical, so you want to limit the amount of water in that acid catalyst that you're adding in those scenarios. So H3O plus would be out. So let's look at our chart here of leaving groups. So we've got our functional groups here in the top row, and then we've got the leaving group that would result from a direct attack of a nucleophile in the second row. So think good nucleophile anionic conditions, and we have an excellent leaving group for the acid halides, conjugate bases of strong acids, and these leaving groups are so good, in fact, that we don't even need acid activation for protonated or weak nucleophiles for these functional groups, including acid anhydrides, which have a leaving group of acetate or carboxylate, which is a weak base, but it's still a leaving group that we can encourage to leave without further activation. Okay, now looking at our next class of compounds here, like we are talking about here, esters and carboxylic acids. So with esters and acids, a good strong anionic nucleophile would require the leave of a hydroxide from a carboxylic acid. But the thing is, carboxylic acids are typically basic compared to other nucleophiles, or acidic compared to other nucleophiles, excuse me. And so when you treat those with a strong base, or even some weak bases, you get a carboxylate, which is the least reactive of all. So we typically don't see hydroxide as the direct or strong nucleophile adding directly to a carboxylic acid without first converting it to a carboxylate. So that is something we will notice in these reactions. Okay, now looking at reactions that form carboxylic acids, okay, a brief run through of reactions we may have already seen before. Ozonolysis of an alkene is going to cut this carbonyl in half, resulting in half of the carboxylic acid, the two carboxylic acids that we see coming from one half of this alkene, and then a second equivalent comes in from the other half of the alkene as well, so times 2 there. And what we're doing with this oxidizing workup with peroxide is every time we have a hydrogen on the alkene of the ozonolysis, we cut in half, creating 2 carbonyls, but then every one of these hydrogens is converted into the hydroxyl on the other end. Okay, and so we get carboxylic acids for these disubstituted alkenes. We get 2 of the same if they're symmetrical, 2 different if the 2 halves are different than one another. So again, we've seen that before. A similar oxidation is potassium permanganate. It does exactly the same thing. Cis or trans alkene, don't let the stereochemistry bother you there. Both of these reactions would result in the same 2 products for both of these alkenes. But potassium permanganate, KMnO4, is a nice easy way to oxidize alkenes to carboxylic acids. We can also use KMnO4 and ozonolysis to oxidize alkynes, excuse me here, so an alkyne to two carboxylic acids as well. And again, the same process, cut the triple bond in half, and then we get our carboxylic acids out of those 3 pi bonds. So 2 carbonyl oxygens and then 1 oxygen for the OH. Okay. Chromic acid oxidation is another way to get a carboxylic acid. We start with a primary alcohol, so right here, and that same carbon results in a carboxylic acid after chromic acid addition. Same thing goes for an aldehyde. So we have an aldehyde here, carbonyl with a hydrogen on the end. We get a carboxylic acid out here. And remember that aldehydes are actually intermediates in the oxidation of primary alcohols with chromic acid. So there are a couple recipes for obtaining chromic acid, H2CrO4. And so I don't care which one of those you use, or you just write H2CrO4 for oxidation of these 2 functional groups to carboxylic acids. Another oxidation method to get to a carboxylic acid is the Baeyer-Villiger. And so an aldehyde will undergo a rearrangement with trifluoroacetic acetate here. And so we have our peroxyacetate. We have a hydrogen that migrates to the outside of this oxygen that's inserted from our reagent. So this is a later reaction, may not be on an earlier exam in the semester, but eventually we will see this as a method for making carboxylic acids. Okay, now a quick review of hydrolysis. Acid halides and hydrides and esters can all undergo hydrolysis with the 2 carboxylic acids. And so we can start with water adding to our acid halide and anhydride. That's a weak nucleophile, strong enough to add to these functional groups, and we will generate an equivalent of carboxylic acid. If we want to use a stronger nucleophile like hydroxide, the first step would actually result in a carboxylate, so an O- on each of these. So a second step to put the proton back on, HCl, aqueous acid, H3O+, would all work for hydrolysis of these 2 functional groups. If we want to hydrolyze an ester, we would treat it with an aqueous acid. So H2SO4 is a good one because it has a non-nucleophilic counter ion, but any aqueous acid will do, and that needs an activation for H3O+, to activate that carbonyl for esters. Now, if we use basic conditions, it's called saponification. We would also require a second step to lower the pH of solution. Again, HCl is strong enough to accomplish this acidification afterward. Otherwise, we'd end up with a carboxylate. Now, if we have an amide, we again want to use protonated conditions, so acidic conditions to activate the amide, H2SO4 and heat, perfectly all right. HCl, aqueous and heat, also fine. So any aqueous acid and heat will do. Or we can use basic conditions in which we would again need a second step. Again, we're still heating with the amide, but we need a second step to lower the pH with HCl, a strong enough acid to protonate that carboxylic acid in the end. We can also hydrolyze a nitrile, and acidic conditions only for this one. So a strong acid and heat and aqueous conditions will hydrolyze that nitrile to the carboxylic acid. Don't forget that the carbon of the nitrile is the carbon of the carboxylic acid that we see at the end. Okay, another way to get a carboxylic acid is a Grignard reaction with carbon dioxide. And so essentially that carbanion acting bond here will add to CO2. Remember, the Lewis structure of CO2 looks like this. So when we add to it, it kicks up an O-, and so we get a carboxylate. And then again a step 2 to lower the pH with HCl, aqueous acid will suffice to make the carboxylic acid in its proton-on form. Okay, another later reaction that again for an earlier exam may not be on our list, so check your list, but for a later exam it will be there. For the final it will be there, the malonic ester synthesis. It's an alkylation followed by hydrolysis and a decarboxylation reaction. And so all three of these steps are required. We deprotonate, preventing transesterification, so we're matching up here and we're getting to a negative charge at this carbon. There's an acidic proton there, mechanism in a different video. And then we perform an SN2 reaction onto our second set of reagents here, an alkyl halide or something with a leaving group. Primary is best, secondary is okay. And then a third step to hydrolyze the esters, and then also to decarboxylate, again, mechanism covered in a separate video. All right, so reactions of carboxylic acids. The first one's the easy one. It's just an acid-base reaction, and so we highlight the bond to OH. We identify our base. Here it's hydroxide. This one goes all the way back to GenChem. And we deprotonate our acidic proton. Equilibrium favors the products here because, again, the difference in pKa is about 10 for these two acids, 15.7 for water, and then about 4 to 5 for acetic acid there. So a big difference leads to favoring the products pretty dramatically. All right. Now, what can we do with that carboxylate once we've got it? Well, we can treat it with thionyl chloride and we can make an acid halide. And so here we can look at this mechanism where we take our carboxylate, the nucleophilic oxygen. So this is a nucleophilic reaction, not an electrophilic reaction at the carbonyl. And we can attack sulfur, kicking off a chloride. So this is tetrahedral sulfur. There's a lone pair there that's typically omitted in most Lewis structures, but it is there. So tetrahedral sulfur, a trigonal pyramidal tetrahedral electron geometry, good candidate for SN2. We kick off that chloride, and now we are set up for the chloride to come back as a nucleophile. It can reverse, it can attack sulfur, or it can attack the carbonyl to kick up to a tetrahedral intermediate, which is also, this is reversible because chloride is a good leaving group. Get sulfur on there. But then the last step's irreversible because if we go forward, we kick off SO2 as a gas. We get our acid halide as that tetrahedral intermediate collapses, but then SO2 bubbles away. Le Chatelier's principle drives this reaction along. The byproducts are there to help us kind of envision how the mechanism proceeds. What we're after here is this acid halide. Same thing with PBr3. Okay, the mechanism is very similar. Don't see it shown very often, so I'll go ahead and do that here. Just to make sure we understand, it's the same as we saw with alcohols. We're just lacking the proton on the OH. PBr3 attack phosphorus, kick off bromide. And then we have O PBr2, bromine comes back around, bromide comes back around, makes a tetrahedral intermediate. Again, we're reversible at this point. Still reversible because bromine's a good leaving group. But an even better leaving group, and one that won't come back to bother us, is OPBr2. And so when that collapses, we kick that off as a leaving group. Phosphorus takes on a dipole nature here to stabilize. We get our acid halide and then OPBr2 with a minus formal charge there on that oxygen. Right, so we can also activate our carboxylic acid by reacting two carboxylic acids together and heating them. So in this particular setup with just heat, we would be distilling away the anhydride, whose boiling point should be much less than the carboxylic acid due to the lack of hydrogen bonding from these OHs that each of the carboxylic acids have. But typically in laboratory conditions, you would throw a drying agent in there like phosphorus pentoxide in order to collect excess water, help drive that equilibrium without the need of distillation. And so we can do that by adding that catalyst. So either way works, but P2O5 and heat might see more commonly in complicated synthesis. Okay, and again, mechanism here, the honors class only, so I'd have that posted separately if required for that particular mechanism. But the Fischer Esterification is fair game, so let's have a look at it. We react the carboxylic acid and alcohol. In order to form an ester, we're going to need acid catalyst here, so H2SO4, HCl, some aqueous acid in order to promote the carbonyl addition. And water removal at the end would be ideal to help drive this to the product, because esters and carboxylic acid share reactivity. They're pretty close. And so you could end up getting a pretty even equilibrium if you're not utilizing Le Chatelier's principle in some way to push this along toward the ester. Okay, so that's just for laboratory. Let's look at the mechanism here. What you would do is say carboxylic acid, alcohol, and H plus, or H3O, or excuse me, not H3O plus, because we're trying to remove water. So this is a non-aqueous acid, okay, just a catalytic acid here of H2SO4. And let's look at the mechanism. So we don't find that we can add the alcohol directly to this carbonyl because of the reactivity level being lower for our carboxylic acid. So a protonated alcohol that's created by the acid-base reaction between H2SO4 and the alcohol would be the proton donor here to our carboxylic acid. I'd allow H2SO4 as well as your proton donor, or just Hb plus. So we could even say that this is the conjugate acid of some base in solution. Not really important what it is. We understand it's probably protonated alcohol, but we can be safe and just put that generic base there. So protonate the carboxylic acid. We're in equilibrium. Now that we're activated, our nucleophile, the alcohol, can come in and attack, making a tetrahedral intermediate. When we look at the tetrahedral intermediate, the carbonyl becomes an OH. There was already an OH there, and then our nucleophile is a protonated alcohol group. Okay, right now the best leaving group is the protonated alcohol, so the only way forward is to remove that proton and deactivate that as a leaving group. That leaves us with a tetrahedral intermediate that has no good leaving group, because they would all form negatively charged oxygen. Carbon's never a leaving group, okay, at least not in any reaction we've seen so far. There are ways, but it's a special point that would be made in that particular reaction. Now, looking at this, we need to activate. We're trying to make an ester, trying to get rid of an OH. So let's activate one of these hydroxyls with our acid that we just got back from the previous step. Now we've got a good leaving group, water, that is different than what we started with, so that leads us towards the product. So if we reform a carbonyl with this hydroxyl, that kicks off water, our good leaving group. And now we see our ester starting to form. So we've got a protonated ester now that we can use solvent or some base from solution there to finally remove that last proton. At no point do we have an irreversible step, but we at least get our ester and regenerate our equivalent of acid to go further promote the reaction elsewhere. Okay, so there's the full Fischer esterification. Again, we've released a water molecule in this step. that we've got to try to take care of by removal at some point. Okay, you've got to use Le Chatelier's principle to either remove the ester or remove water to drive these along. All right, let's look at amide formation. And so right to begin with here, the amide undergoes an acid-base reaction to form an ammonium carboxylate. Okay, and so in a nonpolar solvent, that would end up crystallizing out a nice salt that you could then heat and decompose at some temperature unique to each reaction. Textbooks throw out a guesstimate, but it's fairly unique. Just heat it till you get a liquid back and blow off water, lose water there, and get your amide. And so this will work for a primary or secondary amide. So if you used NH3, we would end up with ammonium carboxylate versus a protonated amine carboxylate. Okay, and then blow off water, H2O, from that primary or secondary amide. No mechanism here, as this is a thermal decomposition. Okay, carboxylic acids also undergo reductions, carboxylic acid to primary alcohol. And so the first thing that we would see in this mechanism is an acid-base reaction to the carboxylate. So aluminum hydride is AlH4 with a formal charge of -1. The bond between one of the aluminum and hydrogen atoms will attack the acidic hydrogen of the carboxylic acid, kicking up the carboxylic acid into a carboxylate. Okay, and so if we show this step as irreversible, because again we've eliminated hydrogen gas, that won't come back, and now we've got aluminum hydride, which is a lot like BH3. Aluminum's right below boron on the periodic table. So here it's got an empty orbital. It wants to act as a Lewis acid, and so the carboxylate will then provide that extra bond to aluminum, setting up here our Lewis acid adduct, which has 3 hydrides left, one of which intramolecularly donates into the carbonyl, kicking up the carbonyl to an alkoxide. It's another tetrahedral intermediate. And so now we've got aluminum with 2 hydrogens now, and it is, here's the hydrogen, it is now needing another bond, and so what ends up happening is this oxygen reforms a carbonyl, kicks off the leaving group here. This leaving group actually has this structure, and it has a resonance contributor then, that if you were to donate this into the aluminum, you would end up filling the aluminum valence to an octet. And so that makes that leaving group fairly stable, and it will not return to bother us. But what we'll see is we have an aldehyde here that reacts faster. Remember, aldehydes react faster than carboxylates, and so we have to add enough lithium aluminum hydride to continue this reaction. With the aldehyde kicking up to an O-. Another tetrahedral intermediate, but this time we have no leaving group on that tetrahedral intermediate. So the only thing to do, we're stuck, is to add acid in step 2 of the line reaction. So at this point, we're adding our acid after we've already added the lithium aluminum hydride. Now we're adding HCl or some strong acid in step 2, or even a weak acid like ammonium chloride would work, but some source of proton here to get our primary alcohol in the end. Again, we're not showing the 2 hydrogens because it's a skeletal structure in that final product. So the primary alcohol. All right. Now, the HVZ reactions, another way to react carboxylic acid, what it makes is an alpha bromo. So there's the alpha bromo carboxylic acid, and it is a sequential reaction between PBr3 and bromine, and then an aqueous workup. That mechanism will be in a separate video because it will fall in a later exam some semesters, and so check your reactions list to make sure whether or not it's on your list.